In this video, I'm going to talk about the comparison test. This is how the comparison test goes. Let's consider two sequences, an and bn. Each of the terms in the first sequence is either 0 or greater. Similarly, each of the terms in the second sequence is either 0 or greater. That means an is greater than or equal to 0 and bn is greater than or equal to 0 for each natural number 1, 2, 3, 4, 5, 6 up to infinity. Now, if that is the case, you can make these two statements, this one and this one. So let's talk about the first statement. If an is less than equal to bn, that means each term in the first sequence is less than or equal to the corresponding term in the second sequence. If that is the case, then summation an will converge if summation bn converges. Once again, if each item in the first sequence is less than or equal to the corresponding item in the second sequence, or each term in the first sequence is less than or equal to corresponding term in the second sequence, then summation an, that means this series an in this case, converges if the series bn converges. Okay, that's the first conclusion. Now let me kind of make some sense out of it. For the first one, we know that this is given, an is less than or equal to bn, right? And also we know that this is bounded below. 0 is less than or equal to an. So now if you apply summation to all of them, right? So let's say I'm going to apply summation. So sum of all the zeros must be 0, right? So that's going to be giving me 0 is less than or equal to sum an, which is less than equal to sum of bn's. Now we know that summation bn converges, right? This is what's given. Then it must be the case that summation an also converges. So that's the first conclusion. Now the second one is kind of the opposite of this, or the flip side of it. So think this time, however, an is greater than or equal to bn, just the opposite of this statement. Okay, an is greater than or equal to bn. All right, then summation an diverges if summation bn diverges. Okay, bn, each term is smaller than an, correct? Now if sum of all the bn's, which is summation bn, diverges, then it must be the case this one diverges too, right? So let's kind of give you an example here. So an is greater than or equal to bn, which is also greater than or equal to 0. Remember these two conditions, these ones. Now you could sum it up over all possible n's. Sorry, there's an n here. Okay, and then what's going to happen? If this guy diverges, okay, if this guy diverges, then it must be the case that something bigger than this should also diverge. That makes common sense, right? Now let me go ahead and give you a couple of examples to help you understand and apply this concept into some of the problems. Let's consider the first example, summation n is equal to 1 to infinity 1 over n squared plus 3n plus 2. And here an is nothing but 1 over n squared plus 3n plus 2, which by the way must be less than or equal to 1 over n squared. Why? Because look at the denominator here. This denominator is obviously bigger than n squared because it has 2 and 3n. So it must be the case that an is less than or equal to 1 over n squared, which I would call bn, my bn. Okay, so an is less than or equal to bn for each n, and also since my n goes from 1 to infinity, it must be the case that each of these terms are positive, right? So there is no negative terms involved. So I could extend it further to the left, saying that 0 is less than equal to an is less than equal to bn. then of course, by the comparison test, we could say that an converges, summation an converges. Why? Okay, we know that summation bn is nothing but summation 1 over n square, right? We know 1 over n square converges, right? But that means what? This summation with an will converge to. So now if I apply the summation to all of them, 0 is less than equal to summation an, right? Is less than equal to summation bn. Of course, summation bn is summation 1 over n square. And this guy converges, so this must converge as well. And of course, this is summation of zeros is just 0, right? So that's the first example. Now let's consider a second example, okay? So this is sort of like a standard example. So summation ln of n over n, okay? Of course, n goes from 1 to infinity. And obviously you can see an here, individual term, an is ln of n over n. All of them are either positive or 0. So we are okay there. Now let me define a term, a sequence bn, which is 1 over n. Now compare an and bn. An obviously is going to be bigger than bn. When is it going to be bigger? When your n is greater than e, okay? Because ln of e, as you know, ln of e is equal to 1, right? So if e is bigger than, n is bigger than e, then ln of n is going to be greater than 1. So we kind of could adjust it a little bit. Maybe we could start it from 3, okay, just to be consistent. In this particular case, the first term or the second term does not become greater than or equal to bn, okay? a1 is not greater than or equal to bn, or b1, or a2 is not greater than or equal to b2. So that's okay. We could chop off finite number of terms in a series without affecting the convergence or divergence of the series. So just keep in mind, we can adjust this thing to n being greater than e, okay? Then all the conditions for comparison test will satisfy. So now, obviously, ln is going to be bigger than 1 all the time, right? When n is greater than e. So that tells you an is greater than or equal to bn, okay? For all n, let's call it greater than e, okay? N is a set of n is a number from the set of natural numbers, okay? N, which is equal to 1, 2, 3, ... Now, of course, summation an then must be greater than or equal to summation bn, which is nothing but summation 1 over n. That is nothing but the harmonic series. But the harmonic series diverges, we know that, right? So summation an must be diverging as well. So in essence, we can conclude that ln n over n diverges. Another example we could consider is this. Let's do another simple example. Summation n is equal to 1 to infinity, okay? Maybe n cube plus 3 over n to the power 5 plus 5. Here the nth term is an is equal to n cube plus 3 divided by n to the power 5 plus 5, which, by the way, is less than or equal to n cube plus 3 over n to the power 5, right? Because there is a 5 here in the denominator, which is going to make the denominator bigger than n to the power 5, because this one is n to the power 5 plus 5. So this statement is true. Now, I can break it down into further simpler form. So n cube over n to the power 5. So this is equal to n cube over n to the power 5 plus 3 over n to the power 5. Now that is 1 over n square, because n cube divided by n to the power 5 is 1 over n square, plus 3 over n to the power 5. Now I could define my bn to be this, okay? Now look, my an, let's go back, an is here. If we go through this sequence of two actions that I have taken over these two lines, right, that concludes that an is less than or equal to bn for all n natural numbers. And also each an is positive or 0, right? An is greater than or equal to 0, and similarly bn is greater than or equal to 0. Then it must be the case that summation an is less than or equal to summation bn, and of course is bounded below by 0, as we talked about already. But we know that summation bn converges, because summation 1 over n square and summation 3 over n to the power 5, both of them converge, right? So if summation bn converges, an must converge too. So this must converge too. So let me summarize what I talked about, the comparison test. If an is greater than or equal to 0, and if bn is greater than or equal to 0, these are two sequences, okay? If summation an is less than or equal to, if an is less than or equal to bn for each n, then summation an is going to converge if summation bn converges. Now the other way around, if an is greater than or equal to bn for each n, then summation an diverges, or is going to diverge if summation bn diverges. And I have given you 3 examples here how to apply these two concepts into solving problems. I hope that this discussion was helpful. Thank you very much.